allow our participants to join us in this not Friday, Thursday afternoon. It's good to see the familiar face. So let's start our session for today. So good afternoon, everyone. It is a real pleasure to open our Food for Sustainability and Grow webinars in this rainy afternoon here in Portugal. But we will be discussing the topic of water management, so probably it's appropriate that it's rain. And today we'll go in more detail about technologies for water purification and water remediation. Yes, it's true. We will go very technical about the topic, but I hope you enjoy our session today. And with me, Claudia Costa, I have the pleasure to have Pedro Martins. Pedro is a researcher at the polymetric membrane from water remediation at Minho University. Christiane Schuster from Fraunhofer Institute for Ceramic Technologies and Systems, the IQTS, and also Mino Negrin, the CEO of NUFiltration, an innovative startup on water purification. I start by giving you a very warm welcome for your availability and for your time to be here with us. Thank you. So before we proceed, let me remind you some house rules. Our webinars are recorded, so if you don't wish to appear on the cameras, so please just keep your cameras off. Of course, we all encourage you to have your cameras on. It's much nicer to see faces than black screens. Again, questions are welcome. I will address the questions to each speaker after their presentations. The questions will be put through slide or through the chat here in Teams. They will be in a written format just by time management purpose. So I have mentioned Slido. Let's give it a try. Let's see how it works. I know that the team has worked on kind of a warm up to this webinar with some questions on Slido. So we will start by going to your browser or on your mobile phone. Just type www.slido.com. You will have an hashtag box, and on that hashtag box, please insert F4S Academy, and you will have two tabs. One for Q&A, which will be the ones where you'll be posing your question, and the other one for polls. And in this poll, the team has prepared a little something about, of course, our speakers' questions. So whenever you are ready, I don't know how many of you have managed to access Slido. Yes, I have a thumbs up by Christiana. Thank you. So let's hear about the first question. Okay, here we go. So the first question relates to strategy to capture heavy metals ions from water. And one of the techniques described here holds quite a lot of potential, particularly due to its simplicity and cost efficiency. Which technique is it? Are we talking about chemical precipitation, filtration, or adsorption? I mentioned that this would be technical, so for those that are not so familiar with these topics, chemical precipitation is when a compound that was in a solution is no longer in that solution, so it's kind of the opposite of dissolving. Filtration is a technique that allows a solid to be prepared from a liquid, passing it through a filter, and you know probably the coffee filters are very familiar to everyone. And adsorption is the addition of molecules of a fluid to a solid surface. So after this great explanation, but I'm sure that Pedro will shed some more light on these definitions. And yes, adsorption is one technique that holds a lot of potential because it can be it's easy to use and can be very cost effective. So well done, everyone. Thanks for taking part. So we managed to go through the first one and the second one, plasmatic sensors. Do you know what they are needed for? Plasmatic sensors. Christiane, you're here. I hope you're ready to shed some more light on this topic. But do you think they are more needed for spectroscopy analysis of pollutants? Are they more in need for detection of molecules on site? Or is it about to ensure that we can achieve the highest water quality possible? And again, we have a clear winner. Christiana, what do you think of our participants? Are they knowledgeable or not? Yes, we have a big thumbs up.
Very well done.
Great, and this was not an easy one, I guess. So, of course, we'll be hearing more about plasmonic sensors, and definitely one of the added values is that they can be placed on site for the detection. Very good. Thank you so much for taking part. Let's move on. And now we go to a question on NUFiltration. I don't know if you have the opportunity to do homework before this session, but do you know what is a key feature of NUFiltration systems? Is it their reliance on green electricity for the full irrigation operation with zero water waste? Or are we talking about the capacity of this system to remove pathogens while at the same time maintaining the micronutrients in the water? Or is it because it's exclusive use in industrial settings for water filtration and sterilization? So we had 1 people voting, 5 people voting, everyone agreeing. We are very consensual. Mino.
Well, yes,
Fine.
very good.
Very good, impressive. So, guys, well done, very good. So this is the topic that we will be addressing here at this webinar. So we have a good warm up, and we kind of have kind of basic understanding of the topic. So I think we're going to have a very productive webinar. And with us, we have Pedro Martins. While Pedro jumps to the stage, let me tell you that Pedro is a doctorate in physics from the University of Minho here in Portugal. And throughout his PhD, he has contributed to several projects, notably to biomimetic microenvironments and point-of-care devices for lung diseases biomarkers. Currently, Pedro focuses on developing innovative polymetric members for water remediation, emphasizing sustainability. He is also known for his expertise in material science and water remediation. Pedro leads significant research projects, including EU-funded initiatives and collaborations between Portugal and Germany. Pedro, it's a pleasure to have you here, and the floor is now yours.
Thank you. Thank you so much. And thank you for the invitation. So I'm going to share my screen.
Yes, it's.
Can you see the presentation?
Yes. No,
okay.
We can see your email. We have your email. It's not really our topic.
Not yet.
Yep.
Okay.
That's the wrong screen.
Oh, are we
Let's
not
try again.
seeing the...
No, I'm seeing we are seeing your email.
Okay, sorry.
Our email to you.
Yes.
So everyone can see that we are very organized. So it probably is best if you stop sharing and start sharing again. Probably select the right screen. Otherwise, Pedro, I think we have your presentation from this end.
I think we lost Pedro completely, huh?
Maybe
Pedro. He used the wrong button, not stop sharing, but
you might
leaving the meeting was the wrong red button.
All right. Okay. So because we don't really know what's happening on the other side, Christiana, are you ready to jump to the floor, and then we'll go back to Pedro?
Sure.
So just a quick introduction to Christiana.
Okay. Yeah.
Okay, so I will introduce Christiane first. So Christiane holds a PhD from Technical University of Dresden, and she specialized in fabrication and characterization of biotemplated nanostructures. Christiane is head of the group Optical Tests, Methods and Nanocenters at the Fraunhofer Institute for Ceramic Technologies and Systems, the IQTS. And since 2011, she performs applied research in the Fraunhofer Society in the field of optical characterization of nanostructures and their development in robust sensors for test and diagnosis methods. Pedro,
connection.
Okay, shall we move to Christiana while you sort your things, or?
No, I think it.
Go ahead, Pedro. If you
Okay.
manage it,
Sorry.
I don't care. I don't care.
All right. Okay.
Can you see the presentation now?
No. We're seeing your email.
Again.
And it's still the same email. I can confirm.
And now?
We're still on the email.
I don't know what.
I think that you should a different screen.
I did the same thing I did before. And now?
No,
I'm not
nothing.
sure.
Let me share the other.
You probably have two screens, right?
Yes, but I did the same thing. I don't know.
Okay, perfect.
Now it's on?
It's on, yes. Not in presentation mode, but it's fine like this. If you want just to
now
press
it is, right?
No, not in presentation mode, but we have your presentation.
Really? And now?
No, but let's move on like this, okay? Pedro,
You can see the presentation like
this? Yes.
Okay, sorry for this.
No worries.
So, good afternoon, everyone. Thank you for the kind invitation. I'm Pedro Martins, as previously presented. I'm here to talk about advanced material for water remediation. I always start giving a background about our context of work. In this case, we are already aware of the relevance of water for life. And Sylvia Earle, one of the first marine biologists, said, no water, no life, no blue, no green. We are already aware of the relevance of water in biology and for life, but we are not that aware about the relevance of water in the economic part. So it is important to notice that water supply, treatment, and distribution sector globally represents something like 70 trillion euro. So I think that the majority of us are not even aware of how much money this is. And if we talk only about water treatment and distribution market, we are talking about 500 or around 500 billion euro. It's a lot of money. So we were aware of the importance for life. We are aware now about the relevance of water for economy. So we do have a problem because the majority of the water that we are using today still is contaminated after the typical classic biological or physical chemical treatments, because we have persistent contaminants that are that resist to this degradation because they are very stable chemically. The majority of them are pharmaceuticals or pesticides that enter the wastewater treatment plants and are released into our water bodies. So to solve this problem that is increasing with population growth and also with the production of different types of chemicals, we need new materials, new technologies that allow us to face this problem.
Pedro, sorry to interrupt. Are you moving on in the slides?
Oh, yes.
No, because it's not showing this. Okay, so.
Okay, of course.
Okay.
So because I have to put like this, right?
Yeah.
Okay.
You need to click on the side.
Okay, sorry. So as I was saying, the economic part of water represents the global market represents about 70 trillion euro it is a lot. I also talked about the water treatment and the distribution market that represents about 500 billion euro. And I was also speaking about the emergent contaminants that now we have to deal with because the traditional treatment methods are not able to degrade them completely. So we do need new strategies, new platforms that allow us to face this problem. And photocatalysis is one of the solutions that we can employ to deal with this. Photocatalysis is very straightforward. We just need a catalyst, a source of radiation, it can be the sunlight eventually, and a contaminant to degrade. When a photon irradiates our catalyst, an electron is excited from the valence band to the conduction band. This initiates a cascade of events that will produce reactive oxygen species on the surface of this catalyst. When these catalysts or nanoparticles, like for example titanium dioxide, are in contact with water, they can interact with the contaminants and degrade them by cutting the bonds, the chemical bonds between them. Ideally, if this process is complete, we will have carbon dioxide and water at the end. Another alternative was already spoke is adsorption. Adsorption is also very interesting, especially for heavy metals, for example, and it represents that the contaminant is not completely eliminated like in photocatalysis, because in photocatalysis the contaminant is degraded, is cutted. In this case, the contaminant normally is just adsorbed to the nanoparticle or other material, and later on afterwards it means that this has to be post-treated. But it's also very interesting for contaminants such as heavy metals. In this case, I'm going to speak more focused on photocatalysis because we know that these materials must be produced. And one of the things that we focus here in our work is the synthesis of nanoparticles. Here is just an example of one of the nanoparticles that you synthesize, photocatalytic nanoparticles, employing titanium dioxide and zinc oxide nanoparticles, functionalized with gold. The idea here of putting gold on the surface of the nanoparticles is to allow these particles to absorb the visible radiation. Absorbing visible radiation means that we can use sunlight, for example, to perform the photocatalytic treatment of water. So normally we produce these nanoparticles through nanoprecipitation. We use a precursor of the gold. We shift the pH to induce the precipitation of the gold into the surface of titanium dioxide. We clean the nanoparticles, and at the end we will have this powder, this pink powder, typical of materials produced with gold nanoparticles, small ones. Okay, we also always tested the influence that the impact that different parameters, temperature, loading of the gold has on the morphology of the nanoparticles, but also in the efficiency afterwards. Okay, we always perform the characterization of the materials, the morphology, the crystalline structure of the materials to understand if it really has the properties that we are looking for, and also the optical properties of the materials to be sure that, for example, this material can be used for instance, the visible radiation. Okay. The last part of the work, normally, in the development of this type of materials, is to test them under different conditions, with different contaminants, with different radiations. And in this case, we tested them with different pharmaceuticals like paracetamol, diclofenac, ciprofloxacin, and hydroxychloroquine. We realized that they have different degradation rates and that they have also different responses with different catalysts. Additionally, we confirmed that these catalysts were able to degrade all the contaminants under visible radiation. Okay, and this was the major achievement of this work, because yes, we want to prove that they are able to degrade under UV radiation, but if we can use the sunlight, it means that the process becomes more cost effective. Okay. Normally, we do a lot of materials with active properties. We can call them smart materials because they have a response to a stimuli. In this case, they respond chemically to the sunlight stimuli. But we know that nanoparticles themselves can be considered emergent contaminants. Therefore, the solution for this case is the immobilization of these nanoparticles into polymeric membranes. The idea is that these membranes represent a substrate, a porous substrate, that allow the percolation of the water through it and the contact between the nanoparticles and the contaminants. So I will give just two examples of two different works that we have already published. So that the idea of developing a membrane with these nanoparticles was the idea that we wanted to perform at the same time photocatalytic degradation of a pharmaceutical like norfloxacin, and also the adsorption of arsenic, all in the same material. This means that we have produced a tricomposite, a composite where we have the yttrium that will be responsible for the arsenic adsorption, and the nanoparticles that will perform the photocatalytic degradation of norfloxacin. Okay, two active materials for two different contaminants, all in the same membrane. That was the biggest idea here. So, as usual, we dispersed both particles, the gold titanium dioxide and yttrium nanoparticles, in the solvent. We added the polymer. At the end, we have a polymer formulation that can be poured into a glass and spread it. After evaporation, we would have a porous structure, which we need to characterize. Okay, we confirm the chemical stability of the membrane despite the loading of these nanoparticles. We confirmed also the thermal stability, and we wanted to know if somehow the wettability of the membrane also changed with incorporation of these nanoparticles. Okay, we always perform these controls. Afterwards, we wanted to test separately the two treatments that we were performing: the photocatalytic one, where we have the norfloxacin degradation, and also the arsenic adsorption, separately first. In the case of the norfloxacin degradation, we tested with UV and visible radiation, and we were able to see that there was a concentration-dependent performance, which means that the highest the concentration of our particles, the highest efficiency we had, without compromising the mechanical and chemical stability as we saw before. The same thing we performed for arsenic, and the result was very similar. The higher the amount of particles, the higher efficiency on the removal of arsenic we achieved. Additionally, in the specific case of arsenic adsorption, we wanted just to confirm if the arsenic was really on the surface, because we are not only using these membranes as the usual physical barrier that membranes are known. So this has other purpose. They have smart materials. So we want to know if the materials are really there. And by ABX, we confirm the presence of arsenic on the membrane after the contact. Of course, ABX is not very accurate for this type of measurements, but we already have an idea of where the arsenic was accumulated on the membrane. Okay. Afterwards, we wanted to perform an assay simultaneously. I mean, the same membrane, the two contaminants in the same solution, and we confirmed the previous results. We were able to remove arsenic. We were able to degrade norfloxacin with both radiations. Okay, and this confirms the multifunctionality of these materials. In a very similar way, we wanted to produce another multifunctional material, another multifunctional membrane, but this time we focused on photocatalytic degradation and antimicrobial properties. To have this dual role, we used, instead of gold, we used silver that can also endo nanoparticles with the ability to absorb visible radiation, and at the same time, silver is also an antimicrobial material. So we focused this time also in the morphology of the polymer, using two different strategies. The same as before, a solvent casting approach, where we have a porous membrane structure, and also electrospinning to have even higher surface area. And we wanted to see if the morphology of the membrane really impacts on the efficiency on the removal of norfloxacin. Again, we can see here the difference of the microstructure of the membranes we are producing. And afterwards, as usual, we performed the tests where we tested both UV radiation and visible radiation on the degradation of ciprofloxacin. We realized that both membranes were also efficient despite the concentration, all of them. And the higher the amount of nanoparticles we added, the higher the efficiency we had for both of them. Both in UV radiation and visible radiation, we realized that the membranes were more efficient, despite the higher surface area that normally the electrospun membranes display. After that, we also wanted to test the reusability of the membranes, because reusability is really, really important for these applications. We need to know that nanoparticles that are immobilized still stay on the membrane after different utilizations, and allow the reuse and do not allow the release of nanoparticles into the aquatic bodies, which represent ecotoxicity. We also confirmed that these membranes were antimicrobial with gram-positive and gram-negative bacteria. The reduction of cell viability was higher in E. coli. And I know that I'm already passing my time. So just to give another perspective for the future, we are now focused on the development of multifunctional membranes that display cell-sensing properties. This means that we are producing membranes that can remediate contaminants, but at the same time, they can also monitor the process with sensors. And for this purpose, 3D printing technologies will be very useful, because they will allow us to produce multi-layer membranes where each one of the layers have a specific function. For example, cell sensing one of them, the other one remediation, and so on. And together with all this, we are performing ecotoxicity tests in all the materials that we produce to avoid the same mistakes that we have in the last decades. We want efficient materials, but materials that do not have a negative impact on nature. So thank you so much for your time. And I'm sorry for this situation, but anyway, if you have any questions, I will be very pleased to help you.
Thank you. It was great. And no worries. We are all very used to technology, and we know that these things happen. And your presentation was very clear. So not to worry about that. So Pedro, I have a question. So it was brilliant, great work that you developed here. It's a bit technical, but it's very interesting. So adsorption methods, they seem to display higher efficiency. They tend to be more versatile, cost efficiency. The sensors that you show, they tend to seem to be simple to operate, require minimum maintenance, and this means that probably they can be deployed in several settings, namely remote areas that otherwise cannot be reached. Still, these adsorption methods are not very widely used in agriculture, particularly if you compare with other industries. So my first question is, in your view, what is preventing agriculture to look into more depth into these sorts of methods?
Yes, of course. I think that these two methods that I spoke about, both photocatalysis and adsorption, they will represent a huge alternative in the future for agriculture and also other purposes, including, for example, drinking water, for example. But each one of them have specific advantages and disadvantages. I mean, adsorption, as I was saying, adsorption does not represent a solution itself. It represents a way of removing the contaminant, for example, from water. Mm-hmm. But afterwards, we will have to deal with it. We will have to desorb from the contaminants, from the materials that we are using, desorb if we want to reuse the material, and then after we have to deal with the contaminants. Photocatalysis.
But at least you have gold and silver in it, so
Exactly.
it's easier.
But photocatalysis can represent, for example, a solution itself, for example, for pharmaceuticals. The pharmaceuticals that we are testing, we can remove from, for example, for antibiotics, we can remove the majority of the antibiotics using photocatalysis. The problem is that the majority of the wastewater treatment plants that are already implemented in our society, they are already very strict. They don't allow us to change a lot the way things are done. So it will require a lot of investment to introduce these technologies into the classical wastewater treatment plants, and eventually also for the agriculture, because agriculture, we know that in some cases we do not need we don't have the same requirements of water quality that we have, for example, for drinking water or water that will be released into the rivers. So this technology can be a good solution, for example, in agriculture.
Okay, that's an interesting. And Pedro, in your views, who would it be the first person you will be knocking on the door to ensure that this technology has wider adoption? So where basically who do you perceive is going to be the main users? Because as you say, there is this mindset, things are very established, the
Yeah,
legislation sometimes is difficult. So and just let me compliment here that, just for our participants, well, something probably more familiar about adsorption methods is, for example, the biochar, which also I
exactly.
believe it works in the same principles, and we also have activated carbon filters and phosphorus absorption materials and silica-based adsorbents. So there are already other
A lot of
technologies.
materials. Now,
Okay, so
regarding absorption, we are focused, for example, in metallic organic frameworks because they offer a combination between organic and inorganic strategies for the same material, and it is very flexible. You can functionalize it. It has a high porosity, so it's very used in absorption technologies. But you were asking about how to make these solutions implemented. I think that we need first to show that they are scalable. And for that, we need to work more with industry and to show, for example, that this process that we use at lab scale to produce these membranes, these nanocomposite membranes, that we can produce them for huge or at least higher volumes and test them in higher volumes, because the volumes that we test here in the lab are like 1-2 liters, and we need to go far beyond that to show that this technology really represents a solution. We know that, for example, for photocatalysis there are a lot of applications, but we do not have that much real implemented stations. We have some pilots in Spain, for example. We have a big one, but we don't have a lot of photocatalytic treatment stations working permanently.
okay, thank you. So on that idea, we have a question here on Slido, and it's actually asking about which stage of the technology you are in, and also if we haven't scaled up the technology, can we make claims that is actually a cost-effective way for water remediation? Can you
Yes, we can.
comment on this?
Yes, because, for example, we now are dealing with very persistent contaminants. For example, PFAs, for example, we were talking about that with Christian the other day. So we do need these technologies. We are now aware that the technologies that we had in the past will not work with these new contaminants that now we are aware. They were already there. They were already there, but now we know that they are there. We know that they are carcinogenic, for example, and we need to have these new technologies to solve these problems. Yes, I think that if we show that this technology is scalable, that we can produce higher volumes and treat higher volumes of water, yes, we show, because we are using polymers with active materials, for example, nanoparticles or metallic organic frameworks that are immobilized. They do not represent any risk for environment because they are there. They do not get out of the membrane. and we can reuse them a lot of times. So I think that this is a real solution for the future. I have no doubts about that.
Okay, Pedro, thank you very much. It's very interesting the work you're doing, very promising. I think you're tackling a very big and important problem here at Food for Sustainability. We are also developing aquaponic systems, so RAS systems, so recirculating the water, ensuring that all the contaminants are removed from the water. So we will definitely are on the watch out for your technology. There's one more question here, but probably I'll move on. I'll come back to this question
Okay, thank you so much,
later
Claudia.
on. Okay, so please stay with us, and we are now called to the floor. Christiane, I already gave a brief overview of your work, so I think we can jump straight into your presentation. Christiane?
Yeah,
Christiane?
we can. I'm here. We
You're there?
can.
Okay,
I'm
great.
on the way to share
Okay,
my
brilliant.
screen.
Because you moved from my screen and
Yeah, sorry,
yes,
I moved
fantastic.
in the house to another place. So there we go. Do you see my
Okay,
screen?
yes, it's perfect. Thank you.
So hello everybody, welcome. Thanks for the invitation. I'll share a bit specifically our work, but in principle also the idea for automated detection of trace substances on site, especially in water, but not necessarily only in water. So in principle, if you have an on-site detection system, this is a data source, first of all, to optimize or to allow process optimization, because if you don't need to grab samples and bring them to the lab, so that you only have data points, concentrations, or whatever water parameter you are interested in at certain moments in time, you will not have a continuous process monitoring, and also, of course, you have efforts to grab the samples to send them, and maybe also the analysis technology is expensive. If you have an on-site, maybe also inline analysis, this will allow you to compare the actual set point of your water cleaning, for example, or for your water process or your process where you want to recycle maybe the water and reuse it several times. And with this parameter, of course, you could also think of controlling energy input that you use for your water treatment, for example. You control chemicals and other resources that you give into the process. You can control the pollutant loads, and at the end, you can make consumers confident if you can prove that your water treatment was giving good results all the time. And with this big picture in mind, as I said, not only for water in water treatment plants as shown here in the upper left, but you can also think, of course, of drinking water. The point becomes even more important if you think about water reuse, not only for irrigation, but also if you reuse your water in whatever kind of industrial process. You want to know if any specific chemicals increase in concentration with every water loop, and at a certain moment they are not helpful for your processes anymore, and you need to stop reusing and exchange the water. Of course, it's also about fermentation processes, which you could better control if you do not need to grab samples. And with that big picture in mind, my group started or is working for a few years already on optical sensors to measure concentration on site in waters. And this sensor system, which is a so-called plasmonic sensor, as in the warm-up already said. So I want to explain a bit how this works, the principle, and then give you some examples we already developed and which are under development to show a bit the different ways you could go with these kind of sensors. So what is a plasmonic sensor? It's based on a nanostructured metal surface or metal nanostructure. In our case, it's this pillar structure as shown in this surface scanning electron microscope picture here. To give that in a more schematic view, you see here a cross section. So you have this nano pillars in the center. Do you see my mouse? I can also share, change, where is it? There we go. So we have here the cross section of the nano pillars. As I said, they have a metal layer on top, and above them there is in a microfluidic channel the liquid analyte that we want to measure. And through this completely system, light is shined through. This usually is a Gaussian spectrum of whatever light source, might be an LED as shown here. And what happens in this nanostructure is that so-called surface plasmons are excited. This is oscillations of the electrons that absorb energy. It's a resonance at the end. And so that means that from this excitation spectrum, this energy, this light is missing, so that we have a gap here in this transmitted spectrum. And the position of this minimum is a characteristic for the refractive index on the surface of these nanostructures. And this principle we can now use to detect if specific molecules bind to this surface, because if they bind, the refractive index is changed, and we can optically measure that by a shift of this minimum position, as is shown here with this dashed line. So that means we need to make sure that molecules that we want to analyze bind to our surface. I'll come to that later. So for that, we usually use a molecular recognition element. But first of all, I want to give some more practical overviews of this sensor surface. So here you see these shifted spectra for different refractive indices on the surface. That's real data, not only principles. And this is then the sensor setup. In reality, I always say it's the size of a cigarette box roundabout. So here you see this so-called sensor chips, what we call it. We have these gray rectangles. These are the nanostructured areas. And then you see here the microfluidic channels. We usually, if we build them in ourselves in the lab, we use this different polymer foils glued on top of each other to design fluidic channels in a geometry, whatever we want to have them. And then you see here the real setup for the principal scheme I just showed. So we have a cover with 4 LEDs to excite these 4 nanostructured areas. Then we have tubings as an inlet and outlet for these microfluidic channels. And on the bottom underneath, there's either electronics or fibers to collect the light and guide them to different kind of detectors. Of course, if you want to use that in an automated manner in a process, you need a bit more to do that optimization. So we have here so-called fluid processors. So at the end, it's just a combination of different pumps that are controlled to have a certain scheme of flushing and washing with different fluids. You can use a spectrometer as a detector, which is a bit larger in size, or you just use this, you see here, printed circuit boards underneath with certain detectors, and you need some bottles to have some washing buffers and to collect the analyte. We only use a few milliliters, so you can use these bottles for weeks with the whole system. And then we built an integrated version. So it has the size of round about a microwave, And this can be used as a standalone device in a lab. And of course, it could also be placed inside an industrial environment. Sorry. So here about this molecular recognition element. So we need something to specifically address only those molecules that we want to detect. So for that, we need to capture them on the surface, to bring them very close to the surface, and usually chemically bind them to the surface to induce this refractive index change. For that, there's a whole palette of different elements available. So you can use antibody-antigen connections. You can use specific DNA molecules, also so-called aptamers, which have a 3D folded structures that is specific to certain molecules. You can use so-called molecular imprinted polymers or maybe even hydrogels. And at the end, of course, you could also think about a combination of different of these recognition elements on different nanostructures, nanostructured areas, so that each area is sensitive for a specific molecule, and you can flush one liquid above all these areas and then in parallel analyze the water for different pollutants or molecules in parallel. So here's one example. That's where we started. So we started with the water treatment plant. So it's the fourth treatment stage, specifically addressing micropollutants. Diclofenac is a very prominent example in academia. So we also started with that. So we developed a certain, it's a so-called indirect immunoassay. I will not go into too many details, but this relies on the interaction with antibodies. So we have a very small diclofenac molecule. In that case, it would be too small to detect directly on the surface because the molecular weight is very small. Therefore, we pre-incubate the treated water from the wastewater treatment plant with diclofenac specific antibodies and have a surface that is diclofenac functionalized. And then these antibodies can bind to the surface or don't bind to the surface if there was no diclofenac present in the pre-treated water. So we get an inverse answer. And we also have a second, as I said earlier, a second nanostructure in each channel as a reference to control for temperature changes and things like that. And that's what then happens. You can really online monitor these changes on the nanostructured surfaces. For example, you see here the reference area, which is not diclofenac functionalized, so nothing should happen here. And as you see that the line stays stable, nothing happens. While on the diclofenac functionalized surface, we have water that carries these antibodies and diclofenac inside. We first flush a buffer to have a stable baseline. Then our water to be analyzed is flushed in. We get an interaction change of this plasmon resonance position. And then we flush with buffer again. And this difference here is then our signal, which is correlated to the concentration of the diclofenac in the water via an calibration curve. And then we can also regenerate the surface, meaning that we flush in usually a different solution with low pH or high salt concentration, for example, to wash away the molecules that have bound earlier, and then the sensor surface is ready for a second cycle. We can do this up to 50, 70, sometimes even 100 cycles. And you see here the whole measurement takes about 15 minutes, depends a bit on the specific analyte, but that's usually a good number, this 15 minutes. So that's much faster than grabbing a sample, bringing bringing it to a lab and maybe have a measurement value every 4 hours or 24 hours. It's not the measurement itself, it's real time, but a complete assay takes about 15 minutes. So it means you would have a concentration value every 15 minutes, which we always call quanti real-time measurement. So here I brought you one of these concentrations curves for specifically for diclofenac. So you see here, this is the area where the so-called working range where the sensor is detecting different concentrations. We can adjust this a little bit depending on different fluidic conditions and assay conditions. In that case, we were aiming here for something between 1 and 10 micrograms per liter. We reached 5 to 14 micrograms per liter. So we usually try to really go for the low concentrations. Not nanograms is not that easy usually. Usually you need to have a pre-concentration step, but this micrograms per liter is usually rather easy to achieve. And we have like 30,000 euro hardware cost. Of course, we are continuously trying to develop this in cheaper versions, but for now it's still cheaper than about more than 100,000 euros, which you usually need to spend for high pressure liquid chromatography, which is then still only a machinery that works in a lab environment and not inside your industrial environment. So with that general overview, I would like to give you some more examples. So one is shown already here. So here we had this like a microwave diclofenac sensor in a container on a water treatment plant. So we on-site controlled a fourth treatment stage based on granulated active carbon. So the carbon was dosed depending on the results of our sensor. We have another project that is focusing on Legionella detection in drinking water. So it's a project together with other companies where we aim to develop such a suitcase, so a mobile measuring kit, which allows to analyze 100 milliliter samples of drinking waters in the different households to check for appearance of Legionella. So depending on, I don't know what the rules in regulations in Portugal are. In Germany, if you have a household with or a house with many parties living in, you once a year need to check the water for Legionella. So all Legionella species and also then specific serogroups. This should happen all in one in this measuring kit. We have we are working on another application which focuses on aquaculture. So in that case, it's salmon aquaculture in Norway. What is the case there is that these salmon can have sea lice or can get ill due to sea lice, which is not good for the fish welfare, and they don't grow that fast then anymore. And therefore, this fish is usually pumped to so-called well boats. That's nothing else than a boat with a big water tank. And there they are treated with certain chemicals at the end, so anti-sea lice agents, to get rid of the sea lice on the surface, on the skin of the fish. And then what nowadays is done is that this treated water is then discharged into the ocean without any further treatment. And then, of course, resistances are growing, and therefore we are trying to develop a treatment technology on board, which is monitored with a plasmonic sensor, so that you can say, okay, after one treatment cycle, all the sea lice agents were removed and degraded, or no, water needs to be treated another cycle so that the concentration is low enough to be discharged into the sea. And you can also think about, in principle, this same technology applies, of course, also to land-based sea farming, for example, for so-called off-flavor compounds. So this is, again, certain chemicals, geosmin, for example, which change the taste of the fish because these chemicals appear in the biofilms on the tanks where the fish is grown. And one last example I brought where we drafted a project and are now about to start a project rather soon is on-site detection of microbiological species. In this specific case, it will be E. coli to be detected in the water from a wastewater treatment plant that is going to be reused for irrigation. This is a rather new subject in Germany. Of course, this is already in Portugal. It's more familiar and much more used than in Germany due to the climate needs. But same story again. So we usually you have a UV disinfection to reduce E. coli bacteria in the water, and this UV disinfection is controlled via our sensor to set the amount of energy that is needed to give a reliable result of the water. And at the same time, you do not only need to detect if there is E. coli or not, you also need to detect if the E. coli is still alive. And so it will be both done in the sensor concentration measurement and viability measurement to ensure water quality for irrigation. And in this process or project especially, we also go in parallel with the so-called co-creation process with the different users, and also to identify other applications besides this E. coli detection. Yeah, that's it basically.
Thank you so
Just
much,
to
Christiane.
give you some ideas, maybe it widens.
It was brilliant. I think there's still some time to mature on all this information, but this was quite interesting. And obviously, we have changed the focus now to more monitoring and control through plasmonic sensors. Christiane, one question. You touch upon that one possibility is to use plasmatic sensors, for example, for nutrient monitoring. So I would turn this to soil nutrient monitor. I believe that the sensors can detect the presence of nutrients and ions, and of course this will have a lot of implications to crop yields and of course environment impact. And also relating to a question that we have in the chat, can you give us a little bit more detail what can be monitored in agriculture and how, for example, here in the chat, in Slido, sorry, we have a question about, for example, herbicides. Can they be detected through this technology?
So what we usually aim for is small molecules. Of course, the larger the molecules, the easier. With small, I mean smaller than a kilodalton, usually as is spoken in molecular weight. So herbicides, fungicides, micropollutants are very prominent examples. So pharmaceuticals, as diclofenac shown. So this would be ideal candidates for this kind of sensors. The advantage is, well, it's specific due to this. If you have a specific recognition element, depending on how good this works, it's it's a targeted analysis. So compared to an electrochemical sensing, for example, it's not the sum parameter. You get really the specific concentration of the molecule you are targeting, and it's easy to integrate on site because it's very small. As I said, cigarette box is the core components, depending on how much automation you need and the specific assay, how much other fluids you need. Yeah, that's maybe basically the answer to that question.
All right. So, okay. So it definitely it's possible, but we need still to be more targets on the nutrients and to do more tests. Also, an interesting question is to understand, because you mentioned several times this is very small sensors, just the size of a pack of a cigarette. But would it be possible to combine these sensors for monitoring and control, but also with the technology that actually destroys these microorganisms?
Yeah, for sure. That's the main idea, to use that sensor not only as a standalone technology, but always in combination with something to treat the water. The sensor itself does not destroy the microorganisms, but it's easy to think about that downstream or in front of the sensor to, I don't know what way to destroy the microorganism, if it would be also with UV light or like UV disinfection or with electric fields. That's easy to combine. Yeah, that's
Okay,
exactly
okay.
the purpose.
So we still need a little bit more development, but there's definitely one of the ways to go. And I will take the third question on slide, also to contextualize a little bit more what we do here at the Food for Sustainability. So we are a collaborative laboratory, and we apply science to real case. At the same time, we have already mentioned here several times that we have financial instruments to support SMEs to adopt any early stage technology. So my question is, imagine that I would like to pilot in my field a plasmonic sensor, for example, for some pathogen detection. How would I go about it? So this is actually relates to in which stage of commercialization are your sensors?
Yeah, I would say we have something like TRL 6 to 7. And Fraunhofer is well dedicated to applied research. So that's exactly what we do. So I would say if you have such an application scenario, you would write me an email, and then we would be your partners together with the other companies, of course, to do the last step together with you to bring this sensor in your whatever farm or greenhouse or water treatment, whatever
Okay,
is the case.
that's very useful, because we have our test beds that are really geared towards TRL 5 and 6. So that could be, very a very good way. We just need to find. Also, I invite here the audience to think about application for plasmatic sensors, but we might start here a good partnership. That's already very good to hear those possibilities. Just one last question, Christiane, and I really need to move on to Mino. So how many times can the sensors be used? One off, and then you
Sorry,
need to
connection
how
was connection was interrupted. You were asking how many times the sensors can
time?
be reused, right?
Yes,
So we have
exactly.
tested it for up to 50 to 7 times, 70 times, sometimes even 100. So now it depends on how often you want to do a measurements, what period and time this is. So if you do it
Okay,
every
so
15 minutes, then it's only like one day. But if you measure only a few hours, then this sensor can be reused for several days.
okay, so it depends on the application. Actually, what
On the number,
we are
on
measuring.
the sequence, the frequency of the measurement. So it's not limited in time. It's limited in numbers of regeneration of the surface chemistry.
Okay, that's very interesting. Thank you, Christiane. Thank you so much for your presentation. I hope
Thank
you
you.
can stay with us. I will move now to Mino. Mino is also with us, and while Mino comes to the stage, let me just introduce you to Mino. Is graduated in industrial engineering and management by the Israel Institute of Technology. He and his father created Nirosoft, which was specialized in the design, production, installation, and commissioning of water and wastewater treatment plants for medium and big size, with the main emphasis, which for the time it was a highly innovative membrane separation process, and we are talking about ultrafiltration, nanofiltration, and reverse osmosis. In 2012, Mino has created NUFiltration water purification process by sterilized mechanical devices. Its technology is based on a worldwide granted patent, which provides for the reuse of sterilized medical device ultrafiltration filters at 3.3 nanomilliliters nominal filtration rate in the field of water treatment. This is something quite interesting. Mino, thank you. I can see that your presentation is already up. Thank you so much, and the floor is now yours.
Well, I think that in 2 words you have summarized all my presentation. So you made my life easier. You can see the presentation on the screen.
Yes, it's working fine.
Okay, very good. So actually, as Claudia has presented the technology, we are speaking basically of ultrafiltration. Ultrafiltration is a very well-known technology in water and other liquid separation. It has been used already for more than 30, 40 years. And it is used mainly in all the applications where filtration and disinfection, mechanical disinfection by removing the infection physically, is required. The main and so the technology might be used in a very, very wide range of applications, but it's not used so widely mainly because of the cost of the final systems. The cost is several times prohibitive even for applications where ultrafiltration might be the best available technology, but it is simply not affordable. So when I was offered from the University of Tel Aviv of this patent, the first thing that I thought about is exactly the possibility to make ultrafiltration affordable and usable for a lot of applications where today it is not applicable. So,
Mino, sorry to interrupt.
yes?
So just to checking that you are moving on in the slides,
No,
because from our end.
I am
Okay,
still there.
thank you.
I am still
Okay,
there.
thank you.
And so I will move to the second slide. Can you see it? Can you see the second slide?
Yes,
Yeah.
we do. We see the second
Okay,
slide.
Yes.
very good. Okay, so what is the patent about? The patent is a very, have to say, very ingenious. I just bought it, so I can say that I didn't think about that. It's very ingenious because we are speaking about the reuse of a device which has been used in the medical sector. So what you see here is a dialyzer, which is actually a membrane, which is used when somebody's kidneys are not working. He's going through a process which is called dialysis. I'm sure that most of you know about what we are speaking about. So basically, what is hemodialysis? Is simply you are arriving to this when fortunately your kidneys are not functioning anymore. You have to remove impurity from the blood, and which is something that your kidneys are not doing. And so you're going to a dialysis center. You sit on a chair. and then they take from you, from your vein, they take your blood, and everything is hydraulically. They connect it to the vein are connected to a pump, a peristaltic pump, which is circulating the blood through this device, which is actually a membrane. Okay, and what you see here is a dialyzer. So what happens into the dialyzers? It is simply a hollow fiber membrane with a nominal rejection rate of 0.003 micron, which is more or less around equivalent to 68 kilodalton molecular weight. The blood enters into this hollow fiber, and then thanks to a process of osmosis with the dialyzer, with this isotonic solution, which is circulating through the membrane itself on the outside of the membrane itself, there is a separation between what has to be retained into the blood, which is the bigger molecules of the albumin, and what has to be expelled from the blood, which are all the low molecular weight molecules, which are the creatine, urea, all the salts like the potassium and sodium, etc. So actually, this is what happens, and in 2-3 hours, the blood is recycled, and the blood is recycled into the body of the patient, while the impurants are being expelled thanks to this mechanical process, basically, and thanks to the size exclusion which is taking place into the membrane itself. Now, what happens after those 3 hours? The patient is going back home. He has to come back in 2 or 3 days. What happens with this dialyzer? What happens with this membrane? So what happens is what you see here on the left side. Okay, on the left side of the slide, 250 millions of those dialyzers, which are used yearly in the world, are simply being wasted. It is a non-degradable waste. It's a medical waste, so it has to be disposed correctly, and that's it. So this is what happens. And but there is a possibility of recycling, reprocessing those dialyzers in the dialysis itself. Meaning that by implementing a medical procedure to sterilize those, which allows to sterilize those dialyzers, you can take them and reuse them in the dialysis itself. But the main problem is that, according to the standard, they have to be reprocessed and reused by the same patient. So if one patient is making the process with a specific membrane, and this membrane is being sterilized. He needs to be retreated with the same membrane. So this is very almost impossible to manage, and therefore almost 98% of the dialysis centers in the world are simply throwing those membranes away. Now the patent, which is really very ingenious, is the following, which has been bought by NUFiltration. So the patent is the following: we take those membranes after let's say those artificial kidneys after they have been used. So we take them not metaphorically, but practically from the waste bin of the dialysis centers. We perform the same sterilization, which is designed in order to reuse those dialyzers in the dialysis, but instead of reusing it as a filter for blood, we reuse it as a filter for water. So actually, why it's so ingenious? Because almost at no cost, because all this process of collecting the dialyzers from from the dialysis center and make the sterilization is is not expensive at all. So at almost no cost, we have in our hands the best filter in the world, the best, let's say, the best ultra filter in the world. Why it is the best ultra filter in the world? Because simply it simulates the best filter in the world, which is our kidneys, basically. So this is the patent, which is today registered worldwide. And how it works? It works in the following way, very simply. We take advantage of the characteristic of the membrane, which means that we use it as a classical hollow fiber membrane, throwing water inside in a dead end mode, throwing water inside. But then what we are interested is not in what remains inside. What will remain inside is all the material which are bigger than the 30 nanometers of the porosity of the membrane. They will remain inside, and what will go out is simply water and salt. So actually, it will be a size exclusion based on the porosity of the membrane. And what happens? It happens when, I'm sure that most of you are familiar with this chart. This is the filtration spectrum. You see the chart here, okay, for 0.003 micron and 0.03. By the way, 0.003 is the nominal filtration rate, and the 0.03 micron is the absolute filtration rate, which means that 100% of the materials which are bigger than 0.03 micron will be rejected completely by the membrane. All those which are between 0.003 and 0.03 will be rejected very efficiently, but not at 100%. Still, it is a lot of components which will remain, which will be rejected by the membrane. And basically, those will be bacteria. All the bacteria are bigger than 0.03 micron. Most of the viruses are bigger than also than 0.03. Most of the organic matters are bigger. So basically, what will happen is that what we will receive from the permeate side of the membrane is water and all the dissolved solids, which are metal ions and eventually also heavy metals, which might be dissolved in the water. So basically, we are speaking about a device which is acting as one of the best ultrafiltration membranes in the market and has almost no cost. So this actually is giving us the possibility to the idea of our company, of our, let's say, of our entrepreneurship, which by the way is already let's say 3 or 4 years in the commercial phase. So we're not a startup anymore, but we are selling worldwide already hundreds of machines per year, and those are our machines. We install those membranes into electromechanical units. So it has a pump, it has all the devices in order to make automatic backwash and all the automatic process. So actually we are selling those machines in fields which until today ultrafiltration was not simply affordable. We are speaking about drinking water in humanitarian field. We are speaking about irrigation in the agriculture. We'll speak about that more deeply in a minute. We're speaking about a tertiary treatment to upgrade secondary effluents to a level of class A effluents. We're speaking about swimming pools, for example, because it is a very interesting application in swimming pools. I will show that in a moment. So, if I might go through maybe very quickly on 1 or 2 applications, we can speak about the application in agriculture, which is actually a perfect fit. I will go through here so that you will understand. Basically, in greenhouses where there is a soilless growing, you are recycling the water. If you want to recycle the water, but first of all, you have to irrigate 100% of the water. The plant is absorbing only 70% of the water. And then you have 30% of the irrigating water, which has to go to the drainage. Now, this 30% of the water, what there is inside, there inside obviously water. The nutrients are over there. The nutrients that you have added into the raw water. But then you have also the risk that some pathogens which might be secreted by the plant can be inside this drainage water. Now, if you want to recycle those waters, obviously you have to remove all the pathogens. Otherwise, you will simply contaminate all the greenhouse. And all the other technologies which are implemented today, UV, ozone, obviously chlorine, etc., are actually killing the pathogens, but are also killing the nutrients, meaning that the nutrients, after being oxidized or irradiated by the UV, for example, are not anymore available to the plant. So actually, if our technology permits, due to the fact that the nutrients are passing through, are smaller than 0.003 micron, but all the pathogens are bigger. So the membrane is selective to exactly to what we want to remove and what we want to leave in the water. So actually, with no chemicals, as you can see from this very simple scheme, with no chemicals, only thanks to the mechanical separation, the physical separation of those membranes, you will receive from the other side of the plant only water and nutrients, and you will remove similarly effectively all the pathogens. Such a system, which is very cheap at the end of the day for the grower, returns pays back in few months only thanks to the fact that the grower is simply saving on water and on nutrients, which are very, very expensive. So this is one of the nicest applications where we are very active. So those are, and then we can go to effluents. In effluents also, this is a very interesting technology.
Just to let you know, sorry to interrupt, just to let you know, we're a bit short on time. So
okay, so I will simply,
minutes.
Yeah, maybe I will simply jump to a small movie. Can I do that?
Sure. Go ahead.
In order to show, okay, I will stop sharing this. In order to show the nicest application of this technology. I hope this will work.
Let me remind you to share also with the sound, Mino, if the video has sounds.
I will try. No, I see that I cannot do that. Oh yes, no, I cannot do that. No, I cannot do that. Sorry. Sorry. So I will go back 1 second to the. No,
Mino,
I can.
If it helps, you can post it here in the chat. We can view it
see?
later on. Yes.
See it now?
Yes.
This is the system which is based on our membranes. And all those systems are dedicated to producing drinking water at a very high level with no chemicals.
Sorry.
And this is the nicest, I think the nicest thing I have ever developed in my life. Sorry for saying that. So this is a small unit, 15 kilos, which contains 8 of our membranes. To throw the pipe into this water, and then you start pumping a very low pressure with the hand pump.
the water moving through.
So
Feel
what
it.
you
It's a bit
receive
harder. Here we go.
is drinking water
Oh wow, that is beautiful. Drinking
with
water. Crystal clear.
no chemicals and no
There you
energy.
go. That is cool. Over here.
And this is something. This is a technique that we have implemented into in humanitarian for humanitarian purposes. People who has no approach to
Once you start to pump the water from the river, you get immediately you will get clean water to drink, and that was like a miracle for the people.
I wouldn't drink from this, but from this I would, yeah.
This is a unit of which costs 1,500 euros, and it can produce water for a village of 400, 500 people, giving drinking water to a whole village. I will show you the end of this. This is the kind of water which the system can purify. And then there is a very nice application in Ghana that the people of the villages were tired of pumping with the hand pump. And so I will show you, will see immediately what they did. So you can see this is the system into a box, okay, into a cage, let's call it like that. And here is the tap, water which is flowing up without anybody who is pumping with the hand pump. So what they did, because they were tired, they simply installed the system in the center of the village. Okay, so people are coming with the buckets in order to fill up the drinking water, and the raw water is stored in this tank at 2 meters height. That's it. And it is enough to purify the water. Here we are. So thank you very much.
Thank you, Mino, and thanks for this great ending. It's really touching to really make a difference in people that really don't have water to drink. And I guess you were on the video, so if you have survived drinking that water, it really shows that the technology works. So
I was in a trip to Ghana with my wife, and I asked her to drink it. So and it was very successful. Yes.
Clever man. Great. Mino, this is actually very interesting, and I really have to say that personally I really enjoy this circularity. You mentioned 2,000 million devices going to waste, so again it's a plus there. But in terms of your technology, you mentioned that, of course, you do purification of water, but probably we are talking that this is more just to systems or places, context where water is expensive. Because you mentioned two things that you draw from your system: water purification and nutrients. I would guess, and examples that you show, that water is actually a scarcity. But for example, in Portugal, nutrients are more of a scarcity. Can you comment on this? Can you tell us the different markets that you have, the different approaches that they look into your technology?
Well, it will take a long time, but I will try to summarize it. Actually, we are aiming different markets. When we are aiming to the let's say the greenhouses. Obviously, we are going to the fact that with this technology, you can first of all circulate water, saving water, which is very important. But on the top of that, you are paying back the system only from the cost of the fertilizers. In 5 or 6 months, you are getting back your investment, because you are saving 30% of the fertilizers. So this is one market. When we go to the humanitarian one, when we are going to, obviously this is a completely different scenario.
Yes, okay, good. Then I think you have different applications here and different beachhead markets for your. Here we are more focused on agriculture. I will turn to Slido because I'm very conscious of time. One of the questions is how does your technology compares with hydrogen peroxide in terms of water disinfection?
Well, hydrogen peroxide is simply oxidizing. We are removing physically. It's very simple.
Okay, and you are also being able to make further use from the nutrients and the residues that you collect.
Yes, if you're speaking about recycling in recycling or sterilizing in agriculture, exactly. Yes, the hydrogen peroxide is oxidizing the fertilizers, and therefore they are not available anymore to the plant.
Okay, great. And now let's go into the costs. How much did it cost 1 liter of drinking water in Africa by using your system?
1 liter. Actually, I cannot even think about a figure because it goes much lower than 0.001 cents. You have only to calculate what is the cost of the hand labor to pump the water, because the filters are lasting for more than 4 to 5 years, and the replacement is something like 80-90 euros, and that's it. So it actually has no cost basically.
Okay, and they are already in use even in Africa. You have the system working in Africa.
We have thousands of systems which are working in Africa, yes, and not only in Africa, in South America, in Asia, in a lot of places.
Okay, good.
Even in Turkey, during the last earthquake, we supplied the water was not available. Simply was not available because all the infrastructure has collapsed, and therefore there was a very big need for something immediate that you can take even water from ponds and manufacturing drinking water. And this is, for example, one of the markets in that we have.
Okay, Mino, you mentioned water saving and water reduction, but do you have some figures of productivity increases, or can you draw any figures in terms of production by using your system?
I don't understand the question. Sorry. What do you
So
mean?
you mentioned and you showed some pictures of greenhouses using the system. So it's clearly some water that can be recirculated into the system, so it doesn't go to waste. But at the same time, you were talking about the nutrients and the ability to reintroduce the nutrients in the water. So this probably means that you have more nutrients in the plants, so they are growing. So it has an impact on crop productivity. Do you have these figures? Can you give us an approximation of this impact?
No, there is no the impact, as I say. Obviously, you are simply taking the water with the nutrients, and you are reusing 30% of the water. Mostly, it goes between let's say 20 and 40% of the water and the nutrients, which are recycled and reused. So basically, you don't need them anymore from the first side from the raw water. This is the main saving that the system is giving.
Okay, good.
There is no actually no impact on the productivity of the greenhouse itself. It has an impact on the earnings of the grower. At the end of the day, he saves a huge amount of money.
Yes, in input costs. Okay, very good. And I believe you have the system also working in Portugal. So if people want to know a little bit more and to see it in action, we can get in touch. I'm sure we'll be able to find a demonstration. Just conscious of the time, just one final question to all our speakers. So we really saw here very interesting technologies and approaches. So I would like just a comment from you all. How could we all combine these technologies to have a better water treatment, water purification systems? And also, if you are aware that difference in the way the price of the water and the incentives for pollute water, mainly in agriculture, should be different so that, these technologies actually are perceived as adding more value to the activity rather than, okay, this is not my problem, there's quite a lot of things, but it will flow to the river or through erosion or will go underwater, so I don't need to look at water treatments. So what are your ideas? First of all, technologies. Can we have this hyper mega super technology, or do we still at this stage need to go in silos? Pedro.
Well, I think that, for example, for agriculture, it is very, very important to invest a lot in sensorization. I mean, we are now working also in the sensorization of the process. For example, developing sensors for humidity of the soils, developing sensors that can degrade themselves using biodegradable polymers that can remotely give us information about the soils. It is very important to combine all this information that we can retain from sensors to the use of the water. I think that agriculture 4.0 is based on this sensorization, digitalization, the involvement of all the process, the irrigation, and the whole monitorization of the process of the irrigation. The quality, the amount of water, all this being inline measured. I think that the crucial thing here is to combine all these aspects, the sensorization, the remediation, and the reutilization of the water into one. I mean, in terms of a general approach that you were speaking about, I think that the three areas that we spoke here can be perfectly combined. I mean, with Christian, we are already combining them. We are using materials to perform remediation or purification of water, and Christian is providing us the ways to monitor all the process. And also the amazing presentation that Mino gave us shows an application, a real application of the material that he's developing with a physical barrier, a physical filtration. I think we can combine all this to achieve even better quality of water and quantity, of course. I think this was an amazing combination already of presentations.
Okay, Pedro, thank you. This is a very positive way to finish. I think, Christiane, you would agree with Pedro, pushing up for more sensors in agriculture.
For sure, I agree. No, however, I would also say that despite of starting from the back end, for me personally, it's more important to start thinking also from the front end, saying where to save pollutants and to tackle them at the source, and not, well, at the end of line when they are already in the river. So
yes,
from a
well,
sustainable point of view,
that's
exactly
a different perspective,
I
but
like
also
my
very
sensors,
important.
yes, but
We shouldn't have pollution at all to start with. Mino,
Well,
your
actually,
views.
yes. Being in the past somebody who built, I have to say, huge plants, the monitoring and the capability to be able to see with your own eyes and immediately online what are the performances of your plant is crucial.
Exactly.
Is crucial. Is very, very important. The only issue that as a constructor, as a, let's say somebody who is building plants and have to sell them, obviously the issue of the price, of the cost of the devices, of the monitoring is very, very important. I mean, at the end of the day, you have to convince your client that it is worth it to install today, for example, a turbidity meter, a turbidity controller, so actually I urge, if I may, I urge Pedro and Christiane to try to achieve monitoring devices, which looks very, very nice. The technology looks very promising at an affordable cost, and then the sky will be the limit, really.
Okay, fantastic. So we have already booked our appointment in 2 years' time to have all
Definitely,
this
yes.
implemented. Ladies and gentlemen, it was a pleasure to have you here with us, both our speakers and our participants. I will now need to call this webinar to an end. Just to let you know, we will be pausing for 1 week, but we'll be back on the 7th of March with another topic, this time functional biodiversity, at the same time, same days in our discussion corner, food for sustainability and grow. Thank you so much and enjoy your evening.
Thank you.
Bye.
Thank you. Bye.
Bye-bye.
Thank you.
Bye-bye.